Alright guys, guess I'm making a Lecture 7 remake today. Somehow my connection, actually you know what, let me check my Wi-Fi. Okay, so I'm connected to the good Wi-Fi. I don't know what happened last time, but apparently my Wi-Fi disconnected in the middle of the upload, so the whole video got lost. I didn't want to leave the class with nothing going into the weekend, so I decided I'm just going to briefly go over kind of a remake of what I did last class. So I have my notes here from last class. It looks like we went over quiz 5 first. This is the first page of the notes. So we went over quiz 5 and I solved it. We went over homework 4, 1C. I think someone had a question about how to find the current once you know the voltages without combining, so we'll go over that. We went over homework 4, 2A, and how to find the voltages without combining. So basically a little bit of stuff from homework 4. Let's review. Some people had questions on this. I'll go back over this. Maybe I'll fully solve it. We'll see. And then I had this disaster of a problem. Sorry, my phone just went off. Had this disaster problem where I got stuck trying to find out why no current flows through that 3K resistor right there. So I've talked to some professors and I'm kind of waiting to hear back from them on their opinions of more or less why this problem seemingly can't be solved with superposition. I solved it with mesh analysis and didn't have any issues. It looks like a normal circuit. I didn't really do anything crazy here, but there's got to be something going on here that's making it very difficult to solve with superposition, because you end up with this situation here. However, this is not very productive if I go over this again. I want to solve it, and eventually I will. However, I didn't want to leave you guys without another example on mesh analysis, so I think I'll do another random mesh analysis problem at the end of this video to send you guys into the weekend prepared to do that homework which requires you to do mesh. So the first thing I'm going to do is kind of talk about the quiz again, that quiz 5. I've talked about this several times now, but I guess the first thing I'll do is go ahead and resolve that quiz. So let's go ahead and set it up. Grounds. So I think one of the main things we talked about in class was that people were having some trouble understanding that this was just a single loop, right? So whatever this current is, this 4 milliamps is what it was on the quiz. So again, this is from quiz 5. This 4 milliamps that's flowing, that flows throughout this whole circuit, and this, because this is just a single loop. So that current flows just like this. So it's flowing up through both of these resistors and it's flowing down through both of these resistors, right? So right off the bat, we already know all the voltage drops across all the resistors by just multiplying the current times the resistance. So this one, since we know the current's flowing down, we know we have higher potential here than we do here. And the same thing with this resistor. And then this one's flowing up, so we know we have higher potential there than we do there, and higher potential there than we do there. Okay. So now we find the voltage drops. We just go 4 milliamps times 2K. That's going to give me 8 volts. 4 milliamps times 1K. That's going to give me 4 volts. And then on this side, 4 milliamps times 2K is going to give me 8 volts. And then 4 milliamps times 1K is going to give me 4 volts. So there's my voltage drops, right? Now I haven't solved for any of the voltages yet. The voltages at any of the nodes. What I have solved for is the drops across each of the resistors. So I think this was V2, this was V1, this was V3, and this was V4, correct? Yeah, I think that's right. So basically, we know all the voltage drops across each resistor. Now we just have to analyze the circuit and see what the voltages are. So what this means, right, this notation, we know the current's flowing down, so we know that the voltage has to be going from a higher potential to a lower potential down through this resistor, right? So V1, basically what this tells me is that I'm starting at a lower potential and I'm going to a higher potential, and this and then this is telling me by how much, right? So I'm starting at 0. I know this is 0 volts, and then I'm going up by 4 volts. So that means that my V1 is 4 volts, right? And then V2, I'm starting at a lower potential, and I'm going to a higher potential by 8 volts. So that means that V2 is 12 volts because it's 4, which is what I'm starting at, and I'm going up by 8. So V2 is 12 volts, and that's that node, right? Now coming over to this side, I'm starting at 0 volts, but the direction of current is telling me that I'm going down by 8 volts, right? I'm starting at a higher potential, which is 0, and I'm going to a lower potential by 8 volts. So that means that V4 is going to be negative 8 volts, because that means that I'm going down by 8 volts, right? And then across this resistor, I'm going down again, but I'm going down by 4 volts. So I'm going to start at negative 8, and I'm going down by 4, and so then I go V3 is negative 12 volts, right? So that's how to solve quiz 5. I've now made 2 videos on it. I think there's a separate quiz video on the website for this quiz. So if you still have problems with this, feel free to ask questions, but there are several resources now for this particular problem. Okay, the next one was homework 4 1C. Right? That was the next one, and that was just a little voltage divider. Where I think I asked you to find the voltages and the currents in these circuits, right? So this was 18 volts. This was the voltage we're trying to find probably, and then you also obviously need to find the current flowing in this circuit. Okay, so this is a voltage divider, so obviously we would use the divider equation. So if I call this V0 or V out, whatever you want to call it, I would say that's equal to 18 volts times 5K divided by the sum of the two, which is 10K. That just becomes a half, so my V out is going to be 9 volts. So that's how to find the voltage, but I think that the question that came in class was how do we find the current, right? So once you have the voltages, that's the great thing about Ohm's law, is that once you have all the voltages, you can find all the currents if you have the resistors, which we do. Because all you need to find, current is voltage across a resistor, and then you need the resistance. And so what you'll notice is that this is a single loop, so the same current is going to flow, through this circuit, this whole loop right here. And so we can find the current either by finding the current through this 5K resistor or by finding the current through this 5K resistor, because those are both going to be the same. So if I did this, the current through here, I would say, okay, I have 18 volts minus 9 volts, right? The difference across the resistor. And then I would divide that by 5K. And then, of course, 18 minus 9 is just 9, so that's equal to 9 volts over 5K, which would give me 1.8 milliamps, right? Also, what you could do is you could just take the voltage across this resistor and divide it by 5K, and that would also give you the current flowing in the circuit. So I've got 9 volts there. I know I have 0 volts here because that's ground. So if I say 9 volts minus 0 volts over 5K, right, that's I. Again, this is I. That's the same exact thing I got here, 9 over 5K, so this is going to be 1.8 milliamps also. So because it's the same loop, right, you can do that. I don't know why my screen's doing that. It's not a face. Alright, so we found the 1.8 milliamps here, we found the 1.8 milliamps there. Basically, if you have a single loop, you can find the current through the 5K up top or this 5K, and it's going to be the same because this is one single loop. Okay? So that basically covers the first page from that lecture. That's quiz 5, and then homework 4 1C. So let me grab another page, and then we'll go on to the next, whatever's next. Let's see what's next. Oh, I think it was from the same homework, but the question now was how do we do the same, like how do we find the current, but without combining the resistors in the other case where we have the current source and the parallel resistors. So let's do that. So looks like it was homework 4 2A. And the problem, isn't this focused? It's like kind of focused. I think it could be better. Let's try some stuff. that didn't work. Yeah, I guess that's as good as it's going to get today. Probably the lighting. Anyways, the problem looks like this. Got current source, 2 milliamps. Then I've got some resistors in parallel. Where this one is 7K and this one is 5K. And then my voltage VA is up top, and I'm basically trying to find the currents using the current divider equation, and then using those currents that I find, I'm going to find VA, right? So obviously we know that this is my I total going into this node right here, or this junction, and that's going to split off into two currents. So let me change colors. So it's going to split off into I1, we'll call them I1 and I2, the current flowing through the 7K and the current flowing through the 5K. So we'll call this one I1 and this one I2, right? And so my current divider tells me that if I want to find, let's say I1, that's equal to my total current times R2 over the sum of the resistors, right? And R2 is, in this case, going to be 5K, so let's just write, this is R2 and this is R1. Basically, if I want to find this current, I use the numerator of this equation is going to be the opposite resistor. And if I want to find this current, then I'm going to use this opposite resistor. So if I want to find I1 first, I can say that that's going to be 2 milliamps, right, times 5K divided by 12K. So let me put that into my calculator, see what we get. 2 times 5 over 12. So I get 0.833 milliamps, and that sounds about right. So that's my I1. Now if I wanted to find I2, I could also use the current divider equation, or I could use KCL. Let's do both, right? So basically, KCL tells me that I1 plus I2 is equal to IT, right? Well, I know I1 now and I know IT, so I could find I2 by saying that it's just 2 milliamps, which is I total, minus I1, which is 0.833 milliamps. Or I could say that I2 is equal to the total, right, times 7K over 12K. This is using the current divider equation. So in either case, 2 milliamps minus 0.833, let's see what that gives me. That gives me 1.167 milliamps. And then if I do the current divider, right, let's try the current divider. So basically 2 times 7 over 12 also gives me 1.167. So basically either would work, 1.167. And that's going to be my I2, so let me write that, 1.167. So now I have my two currents, and now what I need to do is find voltage VA. And so what you can do, since VA is the voltage across the 7K, but it's also the voltage across the 5K, you can use Ohm's law with either one of these resistors and the current flowing through them, and that will give you VA. So basically, if we wanted to use the 7K resistor, we would say that VA is equal to 7K times I1, but VA is also equal to 5K times I2, okay? So 7K times I1 is basically 7K times 0.833 milliamps, and that's equal to 5K times 1.167 milliamps. Right, you don't have to use both. I just want to show you that they're equal. So 1.167 times 5, that's going to give me 5.8333 volts. Right, and then obviously there's going to be some rounding errors, but if I do 7K times 0.833, that also gives me 5.83 volts, right? So they're basically the same. So that we know VA is 5.83 volts, right? So that's how to find the current flowing through, or sorry, how to find the voltage across the parallel resistors using the currents without combining them. You can use either one. You could use the 5K and the current flowing through it, which we did over here, or you could use the 7K and the current flowing through it, which we did right here. So, and they both give me the same answer. I don't know why this won't, just refuses to focus very good today. It's probably the lighting. Let me try and turn the lights on. See what that does for us. Anything good? It doesn't seem to want to cooperate. This room probably just doesn't have great light. Oh, that's not what I wanted to do. Alright, well, let's go back to whatever we had, because that's not going to do it. Oh, there we go. Wow, now it looks really good. Okay, sweet. Hopefully when I switch pages it doesn't get crappy again. So basically I have gone over homework, let's see, I went over homework 4, 1C, I went over quiz 5, and now I went over homework 4, 2A. I think that most of that is the stuff that we covered. Oh, I also went over homework 5, problem 2, which is that big resistor equivalent one. So let's go to that one next. Alright, so that's my second page. Let's go with, I don't know, let's go with teal. So I've got this problem, homework 5, problem 2, right, and basically, okay, there's some guys talking outside, so hopefully you guys can't hear them. We've got this network here. Right, this is basically what the circuit looked like, and then we've got a 10 volt voltage source out here. We've got 1K, 2K, 1K, 2K, all the way down until we get to the end. Okay, so this is what the circuit looked like, and I think that most people would be comfortable with me saying that this first voltage here is 10 volts, right? But we also need to find this voltage here, 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 and here. I don't remember exactly what I called them. Maybe it was V1, V2, V3, V4, V5. So let's just go with that. Alright, and so basically someone in the class said that they used mesh and they made 5 loops here, which that works, you know, that's great. Whatever, like I said, you know, several times throughout this class, is that whatever works for you, that works, unless I specifically tell you in the instructions how to do it or what I want you to use to solve it. Whatever method works best for you is fine with me. So if you wanted to make, you know, a loop for this, a current for this loop, this loop, this loop, this loop, this loop, you'd end up with 5 equations, 5 unknowns. Might be a nightmare to solve, but I'm sure it would go quick because there's only one source. However, another way to solve this is by using equivalents, right? And the first thing you do is you would notice that this 1K and this 1K are in series, right? So you could combine those to make an equivalent resistor, which would be a 2K. So let's go back to the teal marker. And basically my equivalent circuit is going to look something like this, very similar. Except when I get down to the end, I don't have these 1Ks, I have another 2K in parallel with this one because I just combined those. So 2K, 2K, and then you've got 1K, 1K, 1K. Right, this is my equivalent circuit. And you might notice now, right, that these 2Ks are going to be in parallel. Okay, so when I connect all these, those 2Ks are now in parallel. And so a 2K in parallel with a 2K gives me 2K times 2K over 2K plus 2K. So 4 divided by 4, which is just going to be 1K, right? So now, if I draw my equivalent again, right? Now both of these 2Ks are replaced by just the singular 1K that I just found. And so what you should notice at this point is that this is basically my original circuit, but with one of the stages removed. So this is still Vs, which is 10 volts. This is still V1, this is V2, this is V3, and now this is V4. V5 has gone away because we got rid of it when we found this equivalent. That was one of the things that I wanted, basically, I was trying to get accomplished in this problem, was to get you to practice combining these, because you'll notice that when you make resistor equivalents, oh sorry, that 2K is not going to be there. That's just a 1K. When you make these resistor equivalents, you basically end up with some nodes that disappear. And what you do is, if you wanted to find, V5, you basically have to find the current that's flowing through this 2K resistor, and then open it back up to the two 1Ks, and then you'll know the current flowing through this 1K and that 1K, because you know that series resistors have the same current flowing through them. So if I find the current flowing through this 2K, then that would be the same current flowing through these 1Ks, and I could find V5, right? So basically what you're going to do is you're going to keep doing these equivalents all the way down until you get to the end, and then you're going to have Vs, you're going to have this 1K, and this entire equivalent, again, is going to end up as just another 1K. And what you'll get is something that looks like this. This would be your final equivalent, where this is V1, and now V2, V3, V4, and V5 have all gone away. And so what you have to do is, or there's a couple of things you could do, right? You could go ahead now and find the current that's flowing in this circuit, which would be 10 volts over 2K, or 5 milliamps. Right? That's going to be my current. And so you could find V1 by going, okay, 5 milliamps times my 1K gives me 5 volts right here. And now you could split that 1K back up into two 2Ks, right? And, move backwards through the circuit, because this 1K came from the two 2Ks that were in parallel before that. And so you go ahead and work backwards. I went over this in class, but I just wanted to, of course, cover it again. Let me just expand it out a little bit. So if I went and did that, I would have 10 volts. I know that this is 10 volts now. That's 1K. And then if I said that this was my 2K in parallel with this 2K, that might not tell me a whole lot yet. But what it does tell me is that I know that I had 5 milliamps flowing through this 1K, right? That's over here. And so this would be my V1 still, which is going to be 5 volts. So just in case it wasn't clear, I've got 5 milliamps flowing here. And now I know that 2.5 of that is going to flow through this 2K, and 2.5 of it's going to flow through this 2K, right? And so I know that this is 2.5 milliamps. I know that this is 2.5 milliamps. And now I can expand this 2K back out, because I know that 2K came from the previous two 1Ks that were in series. So if I go out here, I'm going to end up with a 1K, a 2K, and then two 1Ks, right? So that would have been, this is me working backwards now. These ... replaced me collapsing this circuit all the way down into this, right? But I'm working backwards now. I know that this is 1K, I know that this is 2K, and now I expanded this 2K back out into the series resistors that it came from. So that would be a 1K, that would be a 1K. I already know that this is 10 volts, right? I guess I neglected to write the source voltage here, but you know it's 10 volts, right? We found this to be 5 volts. We know that this current was 5 milliamps. We know that this current was 2.5 milliamps, and the other 2.5 flows this way, right? So that 2.5 flows down through this 1K, and then we can go, 2.5 milliamps times 1K, that gives me 2.5 volts up here. And so now I found I guess, I don't know if I call this Vs or V0, we found V1, and we found V2, and then we keep going with this process, right? We can keep going down the list, opening these 1Ks back into the 2Ks that they came from, and so on and so forth, right? This 1K came from two 2Ks in parallel, the same way that this 1K came from these two 2Ks in parallel, right? You'll see if you go through this whole process what I mean. I just didn't want to, take up several pages and a bunch of time going over this problem, because I think that you get the gist at this point. So basically, I've gone over a couple problems from homework 4. I went over this problem from homework 5, and now what I want to do last is I want to do one more example of mesh analysis just to leave you with on the homework. I want to see what one I went over last time, so that I don't end up doing the exact same thing, and then I will leave you guys with this video. So let me go ahead and take a peek on the website what I did last time. Sorry, it's going to be here. Current grades, I think it was lecture notes, and I did it on lecture 7, yeah. So I went ahead and already did this one for you guys. Oh, sorry, this is lecture 6. This was just 2 voltage sources configured like that. Okay, so let me go ahead and make one with a current source and do that as an example. Yes, okay, good. It focused. It must like whatever I'm doing right now. So let me this is going to be one last example. I'm going to do a mesh analysis problem, and then I will leave you guys with this. Let's use orange. I don't think I've used orange very much. I'm just going to go ahead and do a voltage source, and we'll do a current source, and then we'll tie everything to ground down here, and that'll be my circuit. Let's go 3K, 2K, 6K, 1 milliamp, and 3 volts. Okay, so that'll be my circuit. And let's say I asked you to find all the voltages and all the currents. So this is V1, this is V2, and then this will be VS. And then you want to find all the voltages and all the currents. Okay, so first what you would do is you would define your currents. You'll notice that I have a current source here, so this makes the mesh analysis problem even easier. And why does it make it easier? Well, first, let's say I define both of my currents clockwise, because that's how I feel like doing it on this problem. So let me first call this I1, and I'll call this I2. And, well, let me write my first equation for my left side loop right here, just because I already know what to do with a voltage source. We may or may not know what to do with a current source yet, but I think you're going to like it. So basically, I'm going to start below the voltage source, is what I always do. I'm going to check from node to node when I go across a component. Am I going up voltage or am I going down voltage, right? So across this 3 volt source, I'm going up by 3 volts. So I'm going to write a plus 3 volts, right? Now across this 3K resistor, I'm dropping voltage. But how much am I dropping by? I'm dropping by I1 times 3K, because that's the current times the resistance, right? My V equals my I times my R, right? And then lastly, I drop across this 2K resistor. And what's the current flowing through this 2K? So this is something you haven't seen before yet, because I haven't defined my currents this way, but you're more than welcome to. I1 is flowing down through this resistor, and I2 is flowing up through this resistor. So they actually, they may or may not cancel each other, but in some form there is some interference, because I1 is flowing down and I2 is flowing up. So previously I defined both of my currents so that they'd both be flowing down through the 2K, or whatever this middle resistor is, so that I would add those currents when I got to this point. In this case, I'm going to subtract I2 from I1, because the current flowing through this 2K is going to be whatever my I1 is minus whatever my I2 is, okay? So I'm subtracting because I'm dropping voltage across the resistor, but the current that's flowing through that resistor is I1 minus I2. So I take that and I multiply it by 2K, and I set the whole thing equal to 0, right? Okay, so we got our first loop. Now for our second loop consists of a current source, and we haven't seen this yet. But That's great. And why is it great? It's great because I don't even need to write a loop equation for this if there's a current source, because the current source and my I2 are exactly the same. So I can literally say that I2 is equal to 1 milliamp, right? Because the current flowing in this loop is set by this current source. So the whole point of writing these equations, right, is to figure out one of the, like, write an equation so that we can get two equations, two unknowns. But this right here is an equation. It's just a very simple equation, right? My I2 is equal to 1 milliamp because I'm literally telling you that the current, the current that I defined is the exact same direction as this current source that was given to me. So now what can I do? I can literally just plug this in for I2, and I can solve this equation for I1, and then I have both my currents, right? So I would say, I would drop this down, and I would say 3 volts minus I1 times 3K, and then I have a minus I1 times 2K, and then I have a plus because I have a minus minus, so plus I2 times 2K. And that whole thing is equal to 0. And I2, right, is just 1 milliamp. So I'm going to let this whole thing be I2 equals 1 milliamp. I ran out of room there. But, so let's plug that in. So I get 3 volts. I'm going to combine like terms here. So I'm going to get minus I1 times 5K. And then plus I2 times 2K. 1 milliamp times 2K gives me 2 volts. Plus 2 volts equals 0. So 3 plus 2 volts gives me 5 volts equals I1 times 5K, right? I divide both sides by 5K. And I get that I1 equals... Sorry, the volts and the K don't cancel. These cancel. So this 5 volts over 5K gives me my 1 milliamp. That's interesting. I made a circuit where they're both 1 milliamp. Did I do something crazy again? Oh my gosh, I gotta put this in spice. Because if this is 1 milliamp and I2 is 1 milliamp, then that means that they can't counter each other and that V1 is gonna give me 0 volts. Holy crap, okay. I think that's what happened. That's ridiculous. So I2 is also 1 milliamp. Man, I got a knack for creating ridiculous problems. Because that would be the case, right? If this is 1 milliamp, this is a 3 volt source. If I have 1 milliamp I1, that means that I drop 3 volts across this, right? And if I drop 3 volts from 3 volts, that means I'm at 0 right here, and no current will flow through the 2K. And then I have 1 milliamp flowing through this 6K, which means I have 6 volts right here. So if I go ahead and solve this, if I go ahead and put this in spice, and that's what happened, I mean, come on, guys. Come on. I might have to start making these problems beforehand, because obviously me coming up with them on the fly is not working out super great. Well, let's see what happens. I'm assuming I didn't make any algebra mistakes, but I guess we're going to find out when I spice it. Okay, so I've got this circuit. I'll ground it in a sec. Let's go ahead and plug in values. So this is a 6K, like I said. This is a 2K. This is a 3K, right? And then I put 3 volts right here. All right, and then this will be, I guess I'll call it VX. This will be VS, and this will be VY. I said VY was going to be 6 volts, VX should be 0 volts. And then, what did I call this? VS. That's obviously going to be 3 volts. So let's run it. If VX is 0 and then the current through R2 is 0, then I solved it properly, but, I need to put 1 milliamp here. But that would be hilarious. DC op. And sure enough, VX is 0. The current through R2 is 0. Okay, so I made another insane problem. This isn't insane, guys. This is totally normal. I mean, I solved it. This could very well happen to you. I just think it's hilarious because I didn't mean for that to happen, and it happened. So, whatever. Anyway, it worked out. So I got my I1 and my I2. They're equal, and since they're basically countering each other, the current through this 2K, right? I told you it's I1 minus I2. It ends up being 0. And if there's 0 current through this 2K, that means that there's 0 volts here because no voltage will drop across it, and we know that this is ground, right? So I've got 3 volts for VS, so if I just wanted to write out all my voltages, if you were solving your homework, you'd say VS equals 3 volts. I called that middle node VX, so VX is 0 volts. And Vy is 6 volts. Oh, I called it V1 and V2 over here, so that's equal to V1, I guess. And that's equal to V2. Alright guys, if you have any questions on this video, feel free to email the group. I just wanted to make something that you guys could go based off of for your homework. Another mesh analysis, and kind of go over what we went over in the lecture for those who weren't there. Have a great weekend, and I will talk to everybody on Monday.